Hey guys, this week we're going to be covering some CCC problems from the 2007 senior set of problems. And this is the first lesson in our 3 lessons, I believe, that we're going to be doing. Just going over CCC problems, how we tackle like the problem-solving nature of them, and what kind of strategies you guys can use for when you guys are actually doing the contest. So, as I said, we'll be going through, today we'll be going through 3 questions, first 3, which is usually where you're actually aiming for in the contest. If you get like first 2, that's already really solid. If you get the 3rd question, then that's even like, that's incredible. You get honor roll actually if you full solve like the first 3 questions. So that's where we're at right now. So we'll be going over our first 3 questions, S1, S2, and S3 on the CCC Senior. I'll be going over S1 and S2, and then Trevor will be going through S3. All right, let's begin. So, problem S1. This is federal voting age. So the problem description is that, okay, so we have a big election on February 27, 2007. Now, this is a fixed date. The government has commissioned an electric voting system, and you've been hired as a subcontractor for this very grand programming project. Your task is to write the system that determines whether a person is old enough to vote. The voting age is 18, so given someone's birthday, you must determine whether that person will be 18 years of age on the day of the election. Now, something to note here that we've just read is that we basically just need to compare whatever their age is given to us with this February 27, 2007 date. So this is like a fixed piece of data. So then one of the next things to be very wary about is the input specification, because this allows you to get a gauge of like how big our inputs are going to be and like how efficient your algorithm needs to be. I think we covered big O before, and just generally a computer can do like hundreds of millions of calculations per second. So just depending on where it scales, you can use an inefficient algorithm or use an efficient algorithm, etc. But we'll see here. Our first number will consist of a number n, so 1 to 100, on a single line, indicating the number of birthdays to evaluate. Okay. Next, the following n lines will be in the form of y, m, d, where y is the year of their birthday. It's only 0 to 2007, because this contest was written in 2007. M is 1 to 12, because obviously there's 12 months, and then d is day. Alright, so output specification. So for each date in the input, we output a line with either yes, if the voter is eligible to vote, or no otherwise. So here's just a sample code. So we're just given 5 birthdays. And this is the first line where it's just their birthday, the year, the date, and the year, the month, and the day. So we'll be going over some sample, just some like going over it. So here's my template code for CPP. I plagiarized this from the competitive programming handbook. This is generally just some basic code. So this include line just includes all of the libraries you'll ever need, so you don't need to do any importing of sort. And also using namespace std, functions like sin and coot and all that stuff are part of namespaces. I won't get into the concept of namespaces, but this just makes it so you have to write less code. And then here's just our main function. iOS sync with Studio just makes it so that inputs are just more efficient, as well as the sin.tie 0. So yeah, this is just some boilerplate I always have. And then the first thing that we have to, I guess, define would be like some variables. So this is just going to be, we're going to be receiving n, and then for each line, we can receive the year, the month, and the date. So then from here, I'm going to just receive the n. Sin is obviously C input. It stands for like C in, so C input, and then coot, which is C out, so C output. And then remember that we need the birthday, not the birthday, the date, February 2007. We need to compare that to this. So we know that this date, the year is equal to 2007, the month is equal to 2, and the day is equal to 27. So from here, I'm just going to write some code just to be able to receive the output, the input actually. So we're going to have a for loop, and this for loop is going to run for each birthday, and then print out the result that we have. So as you know, in just a normal fashion, just for a standard loop, we're going to loop this n times because we have n birthdays to evaluate, I++. And then from here, we can just get some inputs for the next line. So y, m, and then d. So if you guys didn't know, for C++ specifically, with the input, every time we just use these arrow keys, arrow characters, it just goes to the next character, next piece of data. They're all separated by spaces, so that's how it's able to differentiate them. All right. So since for this birthday we have the year, the month, and the date, I'm just going to define some variables: y difference, m difference, and d difference. These variables are just going to be the differences between this date that we're trying to evaluate for and the actual birthday that we have. So I'm just going to copy and paste some code just to be quick about it. So y difference is going to be 2007 minus the year of our birthday. So we're just seeing how many years is the difference, and the month difference, the day difference. So of course, as you can see, m is equal to 2, d is equal to 27 for this date. All right, now here's kind of the logic for this question. So we know for a fact that if someone is of age, if the year difference, if the y difference is larger than 18, if it's like 19, 20, 21, 22, 23, we don't even have to evaluate if like the month and the date, the difference between those. So we don't even need to evaluate that. If they're like if the difference is 17, then yeah, we can just say no or yes. So this question just really focuses on just a bunch of nested if statements, just some logic. So the first type of logic that we can kind of decipher if they're 18 or not is obviously the year difference. So if the y difference is larger than 18, then we can just say yes. Yes, they are 18. Now, just note here, in C++ you can end a line with endl, but I'm just using the new space character because it's just more efficient. All right, the next case is if else if the y difference is equal to 18. So that's where we actually have to evaluate if their birthday is before this date. We'll get into that later. And then the else statement is just that their age is lower than 18. So we can just say no, they are not 18. All right. So now we've determined that that the age difference is 18. We still don't know the month and the date, if their birthday is before this February 27th date. So then we next evaluate the month. And it's just similar to the previous process. So we just determine it like this. So if the month difference is larger than 0, then they're older than 18. If the month difference is like the same, so if their birthday is on February, then we have to look at the day, the specific day. If it's less, then their birthday is obviously after February. So for example, if their birthday is like June, so m would equal to 6. So their birthday is larger. So obviously they would not be 18. So just like before, month difference, and it's just the same structure of code. Else if, and we have m difference is equal to 0. That's where we'll be tackling the day, and then else is just when their m difference is smaller than 0. For statement, we say yes, they're 18. And just note here, m difference is February is like 2, so it's February, and then their month. So it's actually going to be a negative number if their birthday is afterwards. So like I said, June 6, so it's going to be -4. So that's why it evaluates to no, and then for here, it's going to evaluate to yes. So if their birthday is in once again January, then this is going to be this difference is going to be a positive number. So I'm just going to say yes, say no, and then now, like again, we have to look at the day, the specific day. So it's just like the month difference, the comparison, so the 27th to the actual day of your birthday. So if it's after, it's going to be a negative number. So if your birthday's February 31st, it's going to be 27 minus 31, so it's going to be a negative number. That's going to be a no. If it's before, so it's at 23rd, it's going to be positive. If it's equal, then you're also 18 as well. So then what we can do here is if the D difference is larger than or equal to 0, then we know that you're 18. And else, if it's negative, then that means that you were just shy off a couple days in the month for your birthday. So we say, no, you aren't 18. And that completes this question. And then I'll just be putting a sample input into C++. So I'm just using, if you guys didn't know, I'm using VS Code. I'm using an extension, just a code runner, competitive programming code runner, and it just helps out. And passed, like that. So that's the first question that we have. All right. I don't know if there are any questions. I'm kind of just like, I don't know. I don't want to keep you guys for too long, so I don't know if we'll be answering too many questions, just going through, but we'll be posting this afterwards. All right, let's get on to the second question then. So the second question is boxes. So this is going to require a little bit more explanation. Boxes. Nowadays, almost any item can be bought and sold on the internet. The problem is shipping. Before an item can be sent, it must be carefully packaged in a cardboard box to protect it. While items come in many shapes and sizes, finding a box just the right size can be a problem. If the box is too small, the item will not fit. If the box is unnecessarily big, shipping costs will be higher and the item is more likely to move around the box and break. Cardboard box manufacturers offer a fixed set of standard box sizes. Your task is to find the standard box size with the smallest volume into which an item will fit. So each box is a rectangular prism with a given length, width, height. Each item is also a rectangular prism with given length, width, height. An item can be rotated by multiples of 90 degrees in any direction before being packed into a box when it is packed. Its faces must be parallel to the faces of the box. So this is actually a pretty important statement just for like understanding some logic. So what that means, I just have drawn a kind of a diagram. That means we can rotate this box or any item just in any orientation. And what that means is that, as we can see, we have length, height, and width, height, width, and length, width, and height. And there's actually 3 more possibilities. I just haven't drawn them for you. So that means that we can take any combination of length, width, height dimensions, and we can rearrange it because we're able to rotate the box. So then this length becomes the old height. So then this height becomes the old width. So that sort of thing. So that's something to keep in mind as we continue on this question. It doesn't really matter what order the dimensions we have are in determining if this is valid. So we can actually swap the order. So an item will fit into a box as long as its dimensions are equal to or less than the dimensions of the box. So for this statement, for example, I'll just write this down. So we have dimensions 2, 3, and 5. So it will fit if it's 1, 2, and 5. And the reason why is because, so this is the box, and this is the item. So the item dimension just has to be smaller than or equal to whatever this is. Now, another way, just another combination that still works is this. Now, if we're trying to compare if it fits or not, like I said before, the order of the dimensions doesn't matter. So what we can do is we can make it so that this is always in an ascending order, and we can, from that, determine if the box fits just by comparing the first index, just the first dimension to each other. So eventually, this will just become 1, 2, and 5. So we can just compare 2 to 1, 3 to 2, 5 to 5. So that's just where I'm at right now. All right. Input specification. So the first line of input will contain a single integer n, 0. It's to 1,000. So number of different sizes of boxes available. And then the next n lines will contain 3 integers containing the length, width, and height. And the following line will contain a single integer m. M is to 0 to 1,000. It's the number of items to be packaged. The next m lines will contain 3 integers each, giving the length, width, and height of an item. All dimensions will be in millimeters in the range from 1 millimeter to 2,000 millimeters. So output is to consist of m lines, 1 for each item in the input. For each input, output a line containing a single integer, the volume of the smallest box into which the item will fit. The same box may not be reused for any number of items. If an item does not fit in any box, print the line item does not fit. So, sorry for the notification. So basically, the input is saying this. So we have, first, we're going to know that there's 3 different fixed item sizes, item dimensions. 1, 2, 3, 2, 3, 4, and 3, 4, 5. Next, we're given 5 different items that we have to package. So for the first, just like the last question, we're looping through each input. So for this specific item, okay, we have this, and then we're going to check if there's an item box that fits, and then we're going to output the volume. So in this case, this is only 1 by 1 by 1, so it can fit in any of these boxes. And the smallest box with the smallest volume is this. So it's 1 times 2 times 3, which is 6. It's a volume, so it's going to output 6. So that's an example. All right, let's get into some coding then. So as I said before, just the way and the logic that we're thinking is that when we get these inputs of boxes, we can just rearrange them to be ascending order, so it's sorted. And then it's just easy just to compare an item to its box really easily just by checking each index. So let's, I guess, first go through just being able to get the input. All right. So I'm going to define a struct, first of all. And this is just basically me defining a new data type. And it's going to have a length, a width, a height, and a volume. We'll get into why I need to also have the volume in the box, and I can just compute it. If you want to know, it's easier just to have the volume on the box so that I don't have to keep recomputing it. All right. Next, I'm just going to define a global array of boxes, and I'm going to have it size 1,000. The reason why I have it size 1,000 is because we already saw that the input size can only be 1,000, and we'll only be using the first n indexes. CCC, I believe space complexity doesn't really matter, so you can use, like, don't try to use too much space, but you can definitely use a lot of space, and it won't really matter. It's really about the time that you are able to complete something. And in this box, just in this, as you can see, we'll just have 1,000 boxes, and we'll only be using the first n indexes. All right, so let's get into computing our input. All right, so first, I'm just going to define some variables, n, l, n, m, l, w, height, and volume. And then I'm going to have t as a temporary variable. I'll get into why I need that. So I'm just going to get my input, n, and then I'm going to have a for loop just to be able to get these n boxes, like these dimensions, and then store it in my boxes array. Alright, so since I is equal to 0, I is smaller than n, and I plus plus. So then for each box, we need to receive the input. So obviously, it's given to us as 3 separate integers that are space separated. So we can just do L, W, and H, and then I'm going to compute the volume. So it's just going to be L times W times H. Alright, and like I said before, in order to compare these box sizes to the eventual just inputs for these items we're going to have, we want it to be in ascending order. So in order to sort it in ascending order, you could just put it into an array and then use like the sort function. But since it's only 3 items, I'm just going to write some logical statements just to make it faster. So we just need to sort L, W, and H in ascending order so that L is the smallest dimension, W is the second smallest dimension, and H is the largest dimension. So that they're in ascending order, and then we'll be able to input that into into a new object box, and then we'll be able to put it into our array. All right. So I'm basically going to be doing bubble sort in order to sort these. So basically, if we have length, width, and height, we just take length and we compare it to the last item to see if the last item is the smallest item, or which one of them is the smallest. Then we compare this with W to see which one is the smallest. So then after this step, we just have the first item being the smallest number, and then we just have to compare these 2 items to see which one is the largest, and then we'll just move the one number to H, which is the largest, and then we'll have a sorted trio of numbers. So first of all, like I said before, this is just a series of if statements. So if L is larger than W, then we have to swap them. So now this T comes in mind is a temporary variable to store the original value of L, so that we can assign L as the value of W, and then assign the value of W to the original value of L, which is now T. Then this is going to happen again. So if W is larger than H, we want to swap them. And then if L is larger than W, we're just going to swap these values again. All right. So then after this, now that L, W, and H are sorted, we can assign each box its length, width, height, and volume. So since I've already initialized this array as like each index is the type box, all I need to do is I need to just go to boxes and the index I, as we're going from 0 to n, so we're going through like n boxes. That's why we're only using the first n indexes. So boxes.I and then just .l. It's kind of like classes, the syntax. So it's property boxes at that index dot length should be equal to length. Boxes I dot w is equal to w. Boxes boxes dot height is equal to height, and boxes dot v is equal to volume. Okay, so now that we've done this, we also need to sort our boxes in ascending order of volume. And the reason why I want to do that is if we're comparing one of our items to all our box sizes, hopefully we can just go through, we can iterate through each of these, and if we find a box that fits, then we can just stop. We don't have to go through each box size and then determine which one has the smallest volume. We can just stop because we know that at that point, since it fits, it's the smallest volume. So that's why I'm going to be then sorting this. Now, in order to sort this, though, this is a complex data structure. It's like a 2D array, basically. So I'm able to use the sort function, boxes, and then boxes.n. And if you guys didn't know, arrays are basically pointers. So when you type boxes, that's a pointer to the first element, and then boxes plus n is a pointer to the last element. So it's basically saying a pointer to the first element and then to the nth element. But we also need a custom sorting function to only sort it by volume. So compare volume. All right, and then from here, I'm going to define a new function called compare volume. And what this does is it just returns a true and a false when it's comparing two items. And since each item in the array is a box, it takes two arguments, box I and box j. So then all we need to do is return if I is smaller or larger. So then I.v is smaller than or equal to j.v. So we're just comparing the volumes. And this is going to return a Boolean, because this is a logic statement. All right, so now that our boxes are all sorted, and that we can like iterate through them each time we go through an item, now we just need to receive the input for each of our items. So obviously we need to receive the input, how many items we're going to be actually going through, so m, and then loop through m items. If you guys want to know why I'm using I and j for these loops, it's just something that like I'm really used to, and a lot of programmers use. You could use anything, but it's just fast. All right. So from here, I'm going to see the input for a single item, length, width, height. All right. And then I'm going to copy and paste this code for sorting it, because if the item is in ascending order and the box is ascending order, then we're able to compare them. It's just a really easy copy and paste. Okay. Then, when we're here, we just need to compare the box to the item. So we have a for loop, and this loop is going to loop through each box size. So that's why it's going to loop n times, because there are n boxes, not m boxes. And then now, in order to determine if an item will fit in a box, each of its dimensions needs to be larger than or equal to, so let's see here. So boxes, so the jth box dimension that we have, and its L dimension, is going to be larger than or equal to our item dimension. And then we can just have an AND statement. And then we can do that for the width and the height. All right, and then since the item fits, all we need to do is print out the box's volume. The thing is, though, from here, we need to determine if it doesn't fit. All right, so I'm going to add a new variable, item fits, a Boolean, and it's going to be in this loop for each item, this loop. So the item fits. So then from here, I'm going to set item fits equal to true. And initially, I'm also going to set item fits is equal to false. And then if we're able to verify that it fits, then we'll equal to true. And from here, we need to break because we don't want to be evaluating any more boxes that have just a larger volume because we've already determined that it fits in a box that has a smaller volume. So we break out of this for loop. This is what this statement does. So it basically stops this for loop from continuing. And then we just need another if statement. So if the item does not fit, so if item fits, and this is just the not operator, so it's just the opposite, then we just print out item does not fit. All right, so let's just take the sample test case. And the output that we want. Oh, okay. That's an error. I might have typed something incorrectly. Let's see. But just overall, that's basically the code. Let me check. Since we're just like strict for time, I believe the error just has to do with me typing something in being capitalized or not capitalized. So this is just the logic of the code. So now I'll just hand it off to Trevor. Trevor? Yeah. Yes.
Friends. So, in a certain school, it's been decided that the students are spending too much time studying and not enough time socializing. So, to address this situation, it's been decided to give every student a friend. And already at this part of the question, it should signal to us that this is a graph theory problem because the vertices are the students and the edges are like the friendships. And then it says that friendship is one way, which means that it's a directed graph. I underlined that badly. So that is if Janet is assigned to be Sarah's friend, and Janet must be friendly to Sarah, but Sarah's not required to reciprocate. So that's gonna rip Janet. Um, so the assignment of friends is done by computer using student numbers, and every student is assigned exactly one friend. And this piece of information will actually come up later, and we'll come back to it. So sometimes a circle of friends occurs. So for example, if Mark is assigned Fred, and Fred is assigned Lori, and Lori is assigned Jean, and Jean is assigned Mark, then we have a circle of 4 friends containing Mark, Fred, Lori, and Jean. And in a circle, we can say that Mark has a separation of 0 from Fred, 1 from Lori, 2 from Jean, and 3 from Mark. So basically, a circle of friends is just a cycle. And the task at hand is to identify, given the computer assignment of friends, whether 2 students are in the same circle of friends, and if they are, then we need to determine their separation. So, circle of friends is a cycle. Our job is to find out whether 2 vertices are in the same cycle, and if they are, we need to find out how many apart, or like how many vertices apart they are. So, for example, if we had something like this really simple graph, and I just made the students numbers, then this is a cycle because it goes around like this and loops around. And if we want to, let's say, identify if 1 and 3 were in the same cycle, then well, we'd have to find a way to do that, and we need to find out how far they are apart. And just by looking at it, we can tell that they're 1 friend apart. So there's like 2 between them. So 1 and 3 are one friend apart. So before we get started, let's talk about the inputs and the outputs. So the input is a single integer n, which is greater than or equal to 2 and less than or equal to 9,999. And it's on a line by itself, so this is n. And it indicates the number of students in the class. And then the next n lines, so 1, 2, 3, 4, 5, 6. So these lines right here are the computer assignments of friendships. And remember that every student is assigned exactly one friend. Then after that, we get, so following the friendship assignments, there are a series of lines containing two student numbers and separated by a single white space. And these lines, so these ones right here, they represent like the queries that we want to check whether they're in the same circle of friends and their separation. And then at the end, there's like this terminating token piece here that's just 0 and 0. And that tells us to stop the program. And the output, two friends are not in the same circle, then we print no. And if they are in the same circle, then we print yes, and then we print the separation. So let's get started with the algorithm. And I set up a little example graph here with all of us CS Club execs. And so the first thing we need to notice is, so we're going to circle back to here, which is every student is assigned exactly one friend. And that means that there are no branches on each vertex, meaning that each vertex has only one output vertex. So for example, Christian can only go to Yina, and Yina can only go to Aditya. You can't have a situation where, for example, Kevin can go to Michelle and go to Christian. So that's the first important property that we have to notice. And that also means that we can simplify our cycle detection algorithm to be just some spicy graph traversal. So what we're going to do is we take each input, so like this one friend 1 and friend 100, and we assign the first one to be friend 1, and the second one will be friend 2. And then notice that from each vertex, there's only one path that you can go down. So, for example, starting from Yina, you would go from Aditya to Kevin to Michelle to Trevor to Christian, and then back to Yina in a cycle. Or, for example, from Patrick, you would go from Patrick to Calder to Yina to Aditya to Kevin to Michelle, and then all the way back to Yina into another cycle. And this is because there are no branches in this graph, right? Because every student only has one friend. So here's what we'll do. So for example, let's say friend 1 is Kevin, and friend 2 is Trevor. And we want to find out if they're in the same cycle or if they're in the same circle. So what we'll do is we'll start at friend 2. So we start here. And I'll tell you guys why we start at friend 2 in a bit. But basically, we just want to traverse down the path that we can take. And remember that there's only one path. So I go to Christian, then we go to Yina, we go to Aditya, and then we go back to Kevin. And if we hit friend 1, so there's two possibilities, which is we start at friend 2 and then we go down the path and then we reach friend 1. That's possibility number 1. And the other possibility is, for example, if friend 2 was Calder and friend 1 was Patrick, then the path would go down into this cycle and then it would just loop around infinitely without reaching friend 1 or friend 2. And option number 3 is that, for example, if friend 2 is, let's say, is Yina and then friend 1 is Keegan, then we go around and then we reach back to Yina without seeing Keegan. So in those two possibilities, which is we return to friend 2 without seeing friend 1, or friend 2's path goes into a cycle that doesn't include friend 2 or friend 1, then we know that for sure that they aren't in the same circle. And then if friend 1 is on the path downstream from friend 2, then we know that they might be in the same circle. So Trevor is downstream, so downstream in air quotes, because that's what I just call it for the path. Yeah. So we know that Trevor is down the path from Kevin. And then this tells us that friend 1 and friend 2 could be in the same cycle. So all the computer knows right now is that Kevin goes to Michelle, that goes to Trevor. And then there are 3 more possibilities from this, which is that friend 1 and friend 2 are in the same cycle, meaning that they're in the same circle. And the second possibility is that friend 2's path leads into a cycle with friend 1, but it's not a part of it. So, for example, if Calder was, I'll just change colors here. If Calder was friend 1 and friend 2, wait, sorry, Calder should be friend 2, and let's say friend 1 was Christian, then you go down this path and it goes into a cycle that includes Christian but doesn't include Calder. So that's option number 2. And that means that they're not in the same circle. And option number 3 is that F2 leads into friend 1. So let's say Patrick is friend 2 and Calder is friend 1. So friend 2 goes to friend 1, sees friend 1, and then it goes into a cycle that contains neither of them. And that means they're not in the same circle because they have to be in a cycle. And right now they're just in like a little branch that's shooting off of the cycle. So going back to the example with me and Kevin, once we reach Trevor from friend 2, so friend this is F2, this is F1. Once we reach F1 from friend 2, then what we do is we can continue downstream on this path. And if we make it back to friend 2, then it means that they're in the same cycle. But for example, if let's say friend 1 was so if we make it back to friend 1 without seeing friend 2, then it means that friend 2's path leads down to a cycle with friend 1, but is not a part of the cycle. So that would be saying Patrick is friend 1 and Aditya is friend 2. And then what happens is we go down this path and we meet Aditya, and then we go around again, but we don't see Patrick again. We loop back to Aditya. And it means that they're not in the same cycle. And note that since let's see, I'm doing those. So since Trevor's F1, Kevin's friend 2, and we're here and what we want to do is we want to traverse down the path until we go back to friend 2. We can do this actually as we go to each step. We can count the number of steps it takes to get back to Kevin. And that's the separation between the two friends, between friend 1 and friend 2. And that's why we started at friend 2 and not friend 1. And Eric asks what's a friend. Yeah, I haven't heard of those either. So if anyone has any questions about what I just described, if it doesn't make sense at all, make sure to tell me because I'll get started with the coding pretty soon. We're good? Yeah, so just to reiterate, what our algorithm does is we're given 2 friends, and let's say friend 1 is Calder and friend 2 is Keegan. Whoops. Then what we do is actually wait, no, that's a bad example. Friend 1 is Yina and friend 2 is Kevin. Then we start from friend 2. We traverse down the path, and remember that there's only one path because every person only has one friend until we hit friend 1. And once we hit friend 1, we continue traversing down the path until we go back to friend 2. And if friend 2 is on the path, that means that they're in the same cycle. If, for example, friend 2 is not on the path, so we start from Patrick and we go to Yina. We go here, we hit Yina, and then we continue traversing down the path, and all the while we're counting the number of steps. So in case we do actually hit friend 2 again, then we know the distance between friend 1 and friend 2. Then we continue traversing down this path, and we go back to Yina without seeing friend 2. And this means that friend 2 is not in the same cycle as friend 1. And then the final possibility is that both friend 1 and friend 2 are just not in a cycle. And what we do in this case is we just keep track of which vertices we visited. And let's say we visited Yina, and then we visited Dia, and then Kevin, and then Michelle, and Trevor, and then Christian, and then back to Yina. And we haven't seen Keegan or Patrick. Then it means that there's a cycle, but Patrick and Keegan aren't in it. So let's get started with the coding. Yeah, so if you have any questions or concerns, then just make sure to throw them into the chat.
Attendance is open, by the way.
Attendance is open. So Eric asks what data structures I'm planning to use. So at first I planned on using an adjacency list, but since each vertex only has one output, or every person only has one friend, we can actually just use a list. Then each list, so like the index will be the friend, and then the element that the index points to will be the friend of the person. You guys will see more clearly because I'll get started coding right now. First thing we do is we include bits, bit slash stdc ++ .h. Then we use the namespace std. We have our int main, and we return 0 at the end. All right, so here's some terminology we're going to use, which is the friender is the person that friends the friendee, and the friendee is the friendee of the friender's friending. So the friender has to be friends with the friendee, but the friendee doesn't have to be friends with the friender. So the thing is, we take n as the input, so int n and cn n, and this is just the number of students and also the number of connections. Then next thing is we need to figure out a way to store our graph, and like I described before, we can just use a 1D array. But since I hate arrays, I'm going to use vectors instead. We're going to call this vector, or the adjacency vector, next, because each space gives us like the next vertex. For example, you guys probably went over this in the graph theory lesson, right? And yeah, if we look back, oh yeah, this is greater. If we look back to here, the input tells us that n will be from 2 to 999, meaning that or friends, the student numbers will be 1 to 9,999, meaning that we can just make an array that has 10,000 elements, and each of them are integers. And then each of those will represent a student. So let's just do that. We initialize them like this. We can give them a default value of -1 just because. And then we have a second vector of pools, which is called visited. And this is the vector that we'll use to keep track of the vertices that we visited so far. So we'll also need 10,000 of those. And this will be default to false. All right. Yeah. Remember, don't don't be afraid to just speak up or interrupt me if you guys aren't understanding anything, because I'm also going pretty fast given the time right here. So the next thing we do is we need to build the friendships. So we need to take the input. So we'll just use I is less than n, because there are n students and n friendships. So plus I, that's our for loop. We have our ints, which are the friender and the friendee. And I can post a better commented version of this code after the end of this meet. So we take the input. Remember, the inputs look like this. So we have friend 1 and friend 2, and they're space separated. So like Kevin mentioned before, we can just do this thing with CN. Because C++ is nice and it separates the inputs, space separated inputs for us. And then here's the spicy part, which is, so basically each index is a vertex, and then each element at that index is pointing to the next vertex that vertex is connected to. So for example, the friender, I don't know how to say this, the friender, like this index, index friender, will point to friendee. Okay, so now we've built our sort of like adjacency list that tells us what the graph looks like. And then the next thing we need to do is we need to take every single friend query, because, okay, this is really messy. So this part right here, these are all the queries that we get to check whether two people are in the same circle of friends. And remember that it ends with 0, 0. So we have friend 1 on the left and friend 2 on the right. And they're also space separated. So we can just do a while true, an infinite while loop. And then we have int friend 1, friend 2, and we're going to have another one called cur. And what cur is it's just going to represent like the current vertex the computer's at while we're traversing through the list. So then we just do the cn thing again. And then if f1 is equal to 0 and f2 is equal to 0, then that means we've reached the end of the queries, and then we can just break out of this loop. Okay, so the first order of business is we start our algorithm at friend 2. So, so in this case, Kevin and Trevor, then Kevin is friend 1 and Trevor is friend 2, and ignore this one here. We start our search at friend 2, which means that we visited friend 2. So we're just going to set visited f2 is equal to true. And then we can set cur, so the current vertex that we're at, to be equal to next f2. And what next f2 is telling us is, well, next f2 is would be just like Christian. So the friend downstream from the current vertex. And then we have another while loop. So we want to traverse down the graph until current is equal to friend 1, or the current is equal to f2 again, and while we haven't visited the next vertex, sorry. That's right, because if we reach f1, that means what's happened is, here you go. Let's say I went from Trevor to Christian to Yina to Dia back to Kevin, and we've seen Kevin, and that means that there's a possibility that they might be in the same cycle. And if we make it back to f2, so if we make it back to f2 without seeing friend 1, then that means that friend 1 and friend 2 are not in the same cycle. And what happens if we visit a visited vertex without seeing friend 2 or friend 1? That means that there's a cycle that doesn't include neither of them. So to better illustrate this, an example would be friend 1 being Keegan and friend 2 being Patrick. Then you go down here into a cycle with neither of them, and then you revisit Yina, which has already been visited by Patrick before. And that means that there's a cycle without Keegan and without Patrick. Right, so with this while loop, we just say that the visited for cur is equal to true, so we visited the current vertex. And then we set cur to be equal to the vertex that's downstream from the current vertex. So yeah, we're just traversing down the graph until one of these conditions is satisfied or broken. Then at the end, if cur is equal to friend 1, that means that there's a possibility that let me go back to MS Paint. There's a possibility that friend 1 and friend 2 are in the same circle. But we don't know for sure yet. But if current is not equal to friend 1, so if it's equal to friend 2 or is equal to just a previously visited node, that means that it's impossible for F1 and F2 to be in the same cycle. So what we do in this case is we just see out no. Because it tells us that the output should be no if that they're not in the same cycle. But if the current vertex is equal to F1, then the next thing we can do is we make a new variable called distance, and this is keeping track of the distance between F1 and F2. Then we set cur to be equal to next cur. So basically what this is saying is right now we are at Kevin, so cur is right here. And we're setting cur to be equal to Michelle now. And then the next thing we do is we have another while loop, and it's actually the same while loop as above. We continue traversing the graph until we A, reach F1, B, reach F2, or C, we reach a node that we visited before. And I'll go through all these cases on our example graph in a bit. But the next thing we do is we set visited for cur is equal to true because we just visited it. And then we go downstream, so cur is equal to next cur. And then this part we do, we just add 1, we increment dist. Because since we're going from F1 to F2, or we're hoping to get from F1 to F2, we can also keep track of the distance while we're at it. And then at the end of it all, if we manage to return to F2, so if cur is equal to F2, then that means, yes, they are in the same cycle. And what that means is, so cur is now at Michelle, where F1 is Kevin and F2 is Trevor. And cur was able to make it back to F2, where the search started. And it means that both F1 and F2 are in the same cycle. We just print yes. Then with space here. And we can print the distance too, because we were keeping track of that as we were traversing from F1 to F2. Then we can just end the line. And then in any other case, so for example, if cur is equal to F1, and if cur is equal to F1, I actually forget. Oh wait, yeah. So cur being F1 means that, let's say friend 1 is equal to Patrick and friend 2 is equal to Patrick and friend 1 is equal to Yina. Then we meet Yina and then we continue traversing down and we return to Yina. So if cur is equal to F1 here, that means that we've made it to Yina from F2. So we made it to F1 from F2 and we traverse in a cycle and made it back to F1. But F2 is nowhere to be found in that cycle. So that means that they're in different cycles or they're not in the same circle. And if we make it back to a visited node, that means that F2 is equal to Calder and F1 is equal to Patrick. I think. Wait, no. F2 is equal to Patrick and F1 is equal to Calder. And what happens in this case is Patrick makes it to Calder, and then it continues traversing down the graph, and it's visited Yina, and then it goes all the way around back to Yina, which we visited before. And this tells us that Calder and Patrick are not in the cycle that we've reached here. And I'm pretty sure an important property is that because each student only has one friend, then each group of connected vertices can only have one cycle. So basically, Patrick and Calder aren't in the same cycle, and they aren't in the cycle. They aren't in the same cycle, meaning that they're not in the same circle. So in the else case here, we can just print out no. And then the very final step here is at the end of each friendship query, we need to set visited to be all falses again. Because let's say if we had one query here and it was searching for the distance between Kevin and Trevor, then it would go around this entire cycle. Whoops. And it would mark all these vertices as visited. And then if we want to do another query, then we would reach a visited vertex. So for example, we'd go from Patrick to Yina, then we'd see that Yina's already been visited, and then it ends the search. And yeah, that's pretty much it. I'll post a better commented version of this in case you guys want to go through it. And we'll also be posting the video onto YouTube because we always do that. And I guess the last thing we could do is talk about the contest grader. If you guys want to stick around.
We just want to remind everybody here that attendance is up. So if you were in the call around 12:45, make sure to head over to announcements and hit the little white check mark. Thank you.
All right. I think he meant 2:45.
Did I say 12:45? Yeah, I meant 2:45. My bad.
All right. So, I'm assuming most of you guys have already signed up for the CCC. So you guys will have a username and a password. So my username is T24. And then my password is, well, I'm not gonna say it, but I'm just gonna log in. And then you'll get to this screen, which is a table of like all the contests, and then there'll be one of them called CCC 2021, I'm pretty sure. And then over there, then you can just enter the contest and it'll start it for you. I'm pretty sure CCC 2007 isn't in here. So I'm just gonna submit my code to a random problem. And then you can see what it feels like to fail every test case. So 2010, and here's what the contest actually looks like. So usually there'll be a timer somewhere up here and you get 3 hours to do all these problems. And then you can click on any of these problems to view a PDF and the problem description. And then when you want to submit the solution for a problem, you would go down here to this section. Then you would select the problem that you want to submit your solution for. So let's say I'm doing Animal Farm. Then my language is C++11. And then I would select my file, which is this one, which is 2007 s3.cpp. Then once that happens, here, let's do that. Somewhere here. Here we go. 2007 s3.cpp. And then we can press the submit button. And then it'll just say compiling. Then we refresh the page a bunch of times. And it tells us that we have a compilation error because obviously I accidentally put a semicolon, like the smart person I am, in here. I'm gonna make sure this compiles right now. Fingers crossed. Okay, we're good. So how about we try submitting that again? 2007 s3.cpp. Then it tells us to refresh the page a bunch of times, so we do that. And then
Yo.
it says runtime error, segmentation fault. That's right. And I get 0 out of 15 on this problem because the CCC doesn't have 2007.
Yo, Trevor, is this the right problem?
No, it's not the right problem. I'm just showing how the grader works.
Oh, okay.
The solution actually does work though. I can go into demodge. Oops. Demodge. I think it's this one. Oh, that's too far. Here it is, 2007 S3. Then I can submit it here. Okay, this is proof that the solution isn't BS. Unless it is BS. And it says all correct. Yeah, but this is how the actual CCC grader works. So you submit it, and then you refresh it a bunch of times, and then it tells you which cases you got right and which cases you get wrong, but it doesn't actually tell you the actual cases. So yeah, this meeting went a bit over time, but I hope it was helpful. We'll have a couple more CCC practice weeks. I think 2 more before the actual contest. Yeah. And then we'll get to writing the CCC contest.
Yeah, and then I guess that concludes our lesson. Something to note though, guys, I believe next week we won't be doing a lesson, but we're doing a mock, just a mock contest using code forces, I believe. Is that what we're doing, Trevor?
Yeah, we're planning to have a little like a mock CCC, so you can get the feeling, like the feeling of the pressure of the time and how a contest actually feels like.
Yeah.
I'm pretty sure what that thing that I just used, demodge.
Yeah.
This thing has like a mock CCC. Well, somewhere.
Yeah.
Oh wait, yeah.
And also in the CCC grader, you can simulate the contests as well. I believe you can do, if you go back and you look at the contests in the CCC grader, there's timed versions as well, and that just simulates like the timer of the actual contest. There'll be a timer in the corner, and yeah, I guess that's it for us.
Yep. I guess our code will be going up along with the YouTube video. Well, in the Google Classroom.
Yeah, of course. I'll
Tonight.
be posting these two videos. Not these two videos. This lesson on YouTube. And we'll also be most likely posting this code somewhere. All right. Thanks, guys,
All right, well,
again for sticking around. I know it was a long lesson, but we tried our best to condense as much as possible. Hope it was informative. You guys learned something today. Just got an idea about what to do, and overall, happy coding, folks.